Everyone. Let's wait for 5 minutes so that other people can join. Okay. So today we will be discussing some problems related to limit, continuity, and differentiability of some good functions. So in order to start with that, one should be clear about the basic definitions that we will be needing. Okay, so let's start with limit. So when do we say limit x tending to x naught fx is equal to L? If and only if. So we'll start with the basic epsilon delta definition. For any epsilon positive, if we are able to find a delta positive, uh, there exists delta positive such that mod fx minus L is less than epsilon whenever mod x minus x naught is less than delta. That means whenever the points x in the domain are near to x naught, x is in between x naught minus delta and x naught plus delta, the graph of the function, suppose this point is L, the value of the function at these points should be in some neighborhood of L, L minus epsilon to L plus epsilon. So this is the basic definition for limit. Also, we have a sequential criteria. Using that we can all see what is the limit of the function. So then we have the sequential criteria. This is also a very important result, or that one should be aware of in order to study limits. Sequential criteria. It says that again, limit extending to x naught fx is equal to L if and only if for sorry, if mm, if xn is a sequence in the domain is such that xn goes to x naught, then fxn should go to L. That is, whenever xn goes to x naught, fxn must converge to L. So we'll see how we can use these conditions and this definition to look at the limit of some functions. Okay, so let's start with first question. Question number 1. Determine if the limit extending to 0 fx exists for the following functions. The first one is we have f from -1 to 1 to r defined as fx is equal to the greatest integer function. So firstly, let's see how does this function looks like. We all know that this notation, greatest integer function, this is, it gives the value of the greatest integer which is less than or equal to x. Less than or equal to x. So if we want to plot this function, we are from -1 to 1. Obviously at -1 the value will be 1, -1. From open -1 to 0, this will be 0. Then from open 0 to 1, this will be 1. So this is how the function looks like. So what can we say about limit extending to 0? Clearly, using the graph also, one can see that when we approach 0 from the right hand side, the function goes to 1. Whereas when we are approaching 0 from the left hand side, the function is going to 0. So that means the left hand limit and right hand limit are not same, and eventually the limit does not exist. So in this case, mm, uh, clearly the function fx, this is a piecewise function which gives value -1 at x equals to -1, 0 for -1 strictly less than x less than equal to 0. This will be 1 or 0 strictly less than x less than equal to 1. So limit extending to 0 minus. So when we are approaching 0 from left hand side, the function fx, it is a constant function having value -1. So the limit will be -1. And the right hand limit extending to 0 plus fx, again here the function is a constant function, 0, this is 0. Now since limit extending to 0 minus fx is not equal to limit extending to 0 plus fx, therefore the limit does not exist. This is the basic high school concept. I hope you all must have done this such type of questions in your high school, 11 12 standard. So next again we have a good function, we call it the signum function. So part 2, then we have f from again -1 to 1 to r, fx is equal to signum function, signum x. We all know that this function is equal to -1 for x from -1 to 0, it is equal to 0 for x equals to 0, and 1 for x strictly greater than 0. Here also one can see that limit extending to 0 minus fx, this will be -1, and limit extending to 0 plus fx will be 1. So this is also clear that here the limit does not exist. Again, since limit extending to 0 minus fx is not equal to limit extending to 0 plus fx, the limit does not exist. Next, we'll see how we can use the sequential criteria. Next function, sorry. We have if x is equal to sine 1 by x. Here we'll use the sequential criteria to show that the limit does not exist. Let's see how. If we consider the sequence or let's start with suppose the limit exists. Suppose limit extending to 0 fx exists. This implies by sequential criteria if xn sequence goes to 0, then, and suppose this is equal to some L, then this fxn should converge to 0. Now if I take the sequence xn to be such that xn is equal to 1 by 2 n pi and yn be such that yn, this is for every n and n, this is equal to 1 upon 2n pi plus pi by 2. Now clearly the sequence xn goes to 0 and yn also. Clearly this converges to 0 as n tends to infinity. This goes to 0 as n tends to infinity. Then by the sequential criteria, then the sequence fxn and fyn must also converge to L. Or we can say that limit n tending to infinity, limit n tending to infinity fxn should be equal to L, and it should also be equal to limit n tending to infinity fyn. Now let us see what is fxn and fyn. Now fxn, this is equal to, since our function fx is sine 1 by x, so this will be sine 1 by xn. And what is xn? Xn is 1 upon 2n pi, so this is sine 2n pi. And we all know that this is equal to 0 for every n in n. This implies fxn is a constant sequence, basically 0 sequence. So obviously this will converge to 0. We also had that this will be equal to L. So by uniqueness of limit, this L should be equal to 0. Obviously, every convergent sequence can converge to just one point now. L should be equal to 0. Now, let us look at Fyn. Fyn, this is equal to sine 1 by yn. And since yn is 1 upon 2n pi plus, this was 1 upon 2n pi plus pi by 2. So this will be sine 2n pi plus pi by 2. So this is always 1. This implies Fyn converges to 1 because this is again a constant sequence. If I mark this as equation 1, so from here we get, because Fyn also converges to L, and in this case Fyn is converging to 1, therefore again by uniqueness of limit we get L is equal to 1, but this contradicts, but this contradicts our contradicts equation first. Hence, limit does not exist. Because if it exists, then the limit of the sequences fin and fxn must have been same. But in this case, it is not so. Thus, limit extending to 0 fx does not exist. I hope this is clear. Next, let's look at fourth part. We have fx is equal to root x sine 1 by x. Okay. In this case, we will prove that the function has limit again using sequential criteria. In the previous problem, we had seen how we can show that the limit does not exist using sequential criteria. And now let's look at how to prove that limit exists using sequential criteria. So if you remember, in sequential criteria, we should start, if we are proving that the limit exists, we should start with an arbitrary sequence. That means we should show that whenever any sequence which is converging to zeros, xn can be any sequence which is converging to 0, fxn must converge to some fixed L, suppose, say L. So yeah, we'll see how this works in this case. Solution. Now let xn be a sequence such that it is converging to 0, such that limit n tending to infinity xn is equal to 0. Now let's look at fxn. Fxn, this is just root xn sine 1 by xn. So all we need to show is that limit n tending to infinity root xn sine 1 by xn exists. So in order to see that, I will be using the sandwich theorem or the squeeze theorem. Let's see how we can use that. So now, mod fxn, this is equal to mod xn root xn sine 1 by xn. We know that this will be equal to mod root xn times mod sine 1 by xn. Now since mod sine is always less than equal to 1, so this will be less than equal to mod root xn. So from here we get minus, and always obviously root is a positive function, so we don't need to use write modulus every time. So this will be minus root xn less than equal to fxn less than equal to root xn. Now since the sequence xn was converging to 0 using the algebra of limits, we know that root xn must also converge to 0. That means since xn converges to 0, this implies the sequence root xn converges to 0. Also obviously the negative minus root xn also converges to 0. Now since this sequence converges to 0, this sequence converges to 0. Hence now we can apply this squeeze theorem or the sandwich theorem to show that limit fxn will also be 0. This implies by squeeze theorem, which we had discussed in earlier session. This theorem, limit n tending to infinity fxn is equal to 0. No matter how the sequence xn is defined, only the fact remains is that xn is converging to 0. Whenever xn is converging to 0, we can see that fxn is converging to 0. Therefore, by sequential criteria, now since the sequence xn converging to 0, or I should write everything now, since the sequence xn converging to 0 was arbitrarily taken or arbitrarily chosen by sequential criteria, we get limit n tending to infinity, sorry, limit x tending to 0 fx is equal to 0. I hope this is clear. If you have any doubt, you can ask. Okay, then next we have yes, I would like you to try it yourself. Next part, it's almost similar to the above one. Take fx is equal to x cos 1 by x. Again, start with an arbitrary sequence xn that is converging to 0 and see how does this sequence fxn behaves. What will it be, convergent, divergent, or what will happen? Yeah, try this yourself. Okay, next question number 2. Determine if the following limits exist. First part, limit x tending to 0, x minus mod x by x. Second, limit x tending to infinity, x to the power 1 plus sin x. See, in the first part, I would like you to start with firstly observing how does this function look like. So we have fx is equal to x minus mod x by x. We know that mod x is a piecewise function. We have we can define it differently for x positive and x negative. So this is basically x minus x by x when x is positive, because we know that mod x is equal to x whenever x is positive, and x minus minus x because mod x is equal to minus x for x negative upon x when x is strictly less than 0. So this is nothing but 0 for x greater than equal to 0, and this will be 2x by x, so 2 for x strictly less than 0. So now we can clearly look at the right hand and left hand limit. In this case, the left hand limit will be 2 and right hand limit will be 0. Yeah. So, which is not same. So therefore, the limit does not exist. This implies limit extending to 0 minus fx. This will be limit extending to 0 minus 2, and limit extending to 0 plus fx will be limit extending to 0 plus 0, 0, which is obviously not same. This is not equal to 2. Therefore, limit does not exist. Then we have fx equals to x to the power 1 plus sine x. We have limit extending to infinity x to the power 1 plus sine x. When one is looking for extending to infinity, again the sequential criteria will be same. So the sequential criteria will say that whenever xn is tending to infinity, that means whenever, yeah, xn is a sequence which is diverging, we call it a divergent sequence. So the sequential criteria, in this case, sequential criteria for limit extending to infinity fx will be whenever xn is diverging to infinity, then fxn is converging to some fixed L. There's not much difference for if we replace this x naught by infinity, at least for the sequential criteria. Yeah, the epsilon delta definition will have a quite difference. So in this case, one can easily see that using sequential criteria, we can say that this limit does not exist, or we can say that the limit will be infinity. So basically, if I take the sequence, consider the sequence xn such that xn is equal to this is equal to n pi. In this case, what will be our fxn? Fxn will be n pi to the power 1 plus sine n pi. Now since sine n pi is always 0 for all natural n, this will be just n pi. And we know that this will go to infinity as n tends to infinity. Therefore, limit n tending to infinity fxn. Obviously, this does not exist. It is since the sequence is going to infinity, or we can does not exist. This implies by sequential criteria limit extending to infinity, x to the power 1 plus sine x does not exist. Next, I would like you to see, then we have question number 3. Consider the function f(x) is equal to x when x is rational, 1 minus x when x is irrational. We need to look at continuity of this function. Show that the following function is continuous only at x equals to 1 by 2. So for continuity, we all know that in this case the limit should be equal to the value. So basically we say a function f is continuous at x naught. We say f is continuous at some x naught if limit extending to x naught fx is equal to fx naught. So I'll wait for 5 minutes. Just see what is limit extending to 1 by 2. Yeah, because they're asking us to show the continuity at 1 by 2. At other points I'll explain. Just look at x equals to 1 by 2. See what will be the limit of this function. Okay, so you're saying that the limit will be 1 by 2. Because at this point, we'll see how does this function look like near 1 by 2. Solution. We have, now since 1 by 2 is a rational number, 1 by 2 is a rational number, this implies f at 1 by 2 will be 1 by 2. Now let's look at mod f x minus 1 by 2 for x lying in some neighborhood of 1 by 2. Mm. Let x be such that mod x minus 1 by 2 is less than delta. So we are in some neighborhood of 1 by 2, and in this case, mod fx minus 1 by 2, this will be by definition mod x minus 1 by 2 if this x is a rational number, and it will be mod 1 minus x minus 1 by 2 if x is irrational. So this is eventually always equal to mod x minus 1 by 2, which is less than delta. Now this implies for any epsilon positive, there exists a delta which is actually equal to epsilon, such that mod fx minus 1 by 2, this is coming out to be less than epsilon, because yeah, epsilon and delta are same, whenever mod x minus 1 by 2 is less than delta. Therefore limit x tending to 1 by 2 fx, this is equal to 1 by 2, and also this is equal to the value of function at 1 by 2. Therefore the function f is continuous at 1 by 2. Now let's look at other cases. That means what happens when x is not equal to 1 by 2. Now let x not double Okay, now let x naught uh, be such that it is not equal to 1 by 2. Okay. In this case, obviously we know that by density theorem we can always find a sequence of rationals as well as that those of irrationals which converge to x naught. Now by density theorem we can always find x naught xn, find sequences xn and yn such that xn is rational for every n in n, and yn is irrational for every n in n, with limit n tending to infinity, xn is equal to x naught, which is also equal to limit n tending to infinity yn. So basically we got two sequences which are converging to the point x naught. Now suppose if the limit would exist if limit n tending if limit x tending to x naught fx was exist if the now if limit x tending to x naught fx exists, then by sequential criteria limit n tending to infinity fxn should be equal to limit n tending to infinity fin. Now let's see how does the sequences fxn and fin are. Now since xn is rational, this implies by definition fxn is, for rationals the function is fx equals to x, so fxn will be xn. Now since xn is converging to x naught, this implies the sequence fxn converges to x naught. And yn is irrational. This implies fyn, by definition of the function f, this will be 1 minus y. Now by algebra of limits of sequences, we can see that the sequence fyn will converge to 1 minus x naught because yn is converging to x naught. This implies, now let me mark this as 1. This implies by first x naught, this is equal to 1 minus x naught, which implies x naught is equal to 1 by 2. But we started with x naught not equal to 1 by 2. But since x naught is not equal to 1 by 2, we get a contradiction. Therefore, limit x tending to x naught fx does not exist for x naught not equal to 1 by 2. I hope this solution was fine. I would like you to go through this solution once again, and if you have any doubt you can ask. Yeah, this is still 1 by 2, the limit is 1 by 2, that was clear. What happens for the case x naught not equal to 1 by 2? Yeah, you can, if you want to see guess the point where the functions where the limit exists. This is basically where the rationals and irrationals are equal. Whenever we have a function of this form, suppose this fx is equal to gx for rationals and hx for irrationals. So the limit actually exists whenever this gx is equal to hx. In this case, this was whenever x is equal to 1 minus x. Basically, x equals to 1 by 2. So these are very special kind of functions. Taking this gx is equal to minus 1, we call this as a Dirichlet function. So this mainly happens due to the density of the rationals. We know that rationals are dense in a real line. So yeah, I hope this is fine. You got it? How do we guess the point? Okay. So next comes the uniform continuity. We started with limit, then we have continuity. Next comes the topic of uniform continuity. So I'll just recall the definition. Uniform continuity. So we say a function is uniformly continuous. So firstly, we always say a function is continuous at some point. We say we look at continuity at some point x naught. We see limit at some point x naught whenever extending to x naught. So limit and continuity are we call them point based properties. But when it comes to uniform continuity, it is domain based property. So basically, it something must happen domain of the function. For continuity and limit, we wanted to see only neighborhood. We just needed the neighborhood of some point. So yeah, that was point based property. But here we say that a function is uniformly continuous, and we say a function is continuous at some point. So yeah, we say a function is uniformly continuous if we say a function f, which is defined from say x to y, x and y some subsets of R, is uniformly continuous if for any epsilon positive we can find there exists delta positive such that mod fx minus fy is strictly less than epsilon whenever mod x minus y is less than delta. That means whenever 2 points any the domain are very near to each other, the value at those points should also be very close to each other. So this should happen for every xy for any point in the domain x. Then again, as we had seen earlier, the sequential criteria, we can also see uniform continuity using sequences. So yeah, you can call it sequential criteria for uniform continuity. Mm, do we have other colors? Yes. Sequential criteria for uniform continuity. It says that if xn and yn are two sequences, if xn and yn are two sequences such that the sequence xn minus yn is converging to 0, then oh we should not call it the sequential criteria. This is just a result for uniformly continuous functions, because in sequential criteria we had if and only if a sequence is sorry, a function is continuous if and only if the sequential criteria holds. So we should call it just a result. If xn and yn are two sequences such that xn minus yn is converging to 0, and f is a uniformly continuous function, and f is uniformly continuous function, then the sequence fxn minus fyn should also converge to 0. I hope you understood why I am saying that this is not if and only if statement. In this case, yeah, there might be some sequences xn and yn such that fxn minus fyn is converging to 0. That does not imply that the sequence is that the function is uniformly continuous. Only if the function is uniformly continuous, in that case, this should hold. So yeah, we'll see how we'll use these results. Okay, so let's look at some functions. Next we have question number, this was 3, 4. Determine which of the following functions are uniformly continuous in the interval mentioned. Determine which of the following functions are uniformly continuous in the interval mentioned. First, we have fx is equal to e to the power x square sine x square, and our domain is open interval 0 to 1. Sorry. Solution. Okay, so for this, one must be aware of a result of uniformly continuous functions. I'll just recall that. If okay, we are working on the set of real numbers now. If f is a function from closed interval ab to r, then and it is continuous, then it is automatically uniformly continuous. It happens only if the domain of the function is a closed interval. It's continuous, then f is uniformly continuous. So if a function is continuous, So if a function is continuous on closed and bounded uh, set domain, then it is uniformly continuous. It can be replaced by any closed and bounded domain. Closed, and I hope this must have been discussed in your theory lectures. A function continuous on closed and bounded domain is always uniformly continuous. So in this case, we know that the function fx is equal to e to the power x square sine x square is always continuous. So this will be, since fx is equal to e to the power x square sine x square is continuous for every x in R. This implies f is continuous on close interval 0 to 1. Now, since it is continuous in close interval 0 to 1, close interval 0 to 1 is again closed and bounded domain. This implies f is uniformly continuous in close interval 0 to 1. We want to see what happens for open interval. Now, since open 0 to 1 is a subset of closed 0 to 1, and also uniform continuity is a domain based property. Now, since function is uniformly continuous on larger domain, it must be uniformly continuous on the smaller domain as well. This implies f is uniformly continuous in open interval 0 to 1. That's the main idea of this question. We use the continuity of the function on closed interval 0 to 1. Next, we have fx is equal to mod sin x. Just see whether this will be uniformly continuous or not. Use the basic definition that we started with, this one, to see whether the function is uniformly continuous or not. I'll wait for 5 minutes. You can try yourself. Yes, it will be uniformly continuous. Um, yeah, let's see how. Okay. Now for any x and y. Now, yeah, we'll start with any x and y. In close interval 0 to infinity. Mod fx minus mod fy. This will be equal to mod sin x minus mod sin y. We know that mod a minus mod b is less than equal to mod a minus b. So this will be less than equal to mod sin x minus sin y. And this happens because mod a minus b, this is less than equal to a sorry mod a minus b. Now this tells us, now this is equal to, using sin x minus sin y, this will be equal to 2 cos x plus y by 2 times sin x minus y by 2. Yeah, this is basic sin a minus sin b property. So this will be equal to 2 mod cos x plus y by 2 times sin x minus y by 2. We know that value of mod cos x is all mod cos a is always less than equal to 1. So this will be less than equal to 2 times mod sin x minus y by 2. Now this happens because mod cos x plus y by 2, this will always be less than equal to 1. Now this is less than equal to 2 mod x minus y by 2. This happens because we know that mod sin x is less than equal to mod x. Now this is equal to mod x minus y. Now if I take x and y such that mod x minus y is less than delta, I will eventually get mod fx minus mod fy is also less than delta. Taking delta equal to epsilon, taking delta equals, let me mark this as equation 1, equal to epsilon, we get mod fx minus fy is less than equal to mod x minus y, which is strictly less than delta, equal to epsilon whenever mod x minus y is less than delta. Now this gives us that for any epsilon positive, there exists delta which is equal to epsilon positive such that mod fx minus fy, this is less than epsilon whenever mod x minus y is less than delta. This gives us the uniform continuity. Therefore, f is uniformly continuous on close 0 to infinity. I hope this proof is clear. If you have any doubt at any step, please let me know here. Yeah, because our domain was close 0 to infinity, which can never be a subset of some closed and bounded set. We could not use the continuity of the function sin x, mod sin x. So we had only one choice, to use the definition of uniform continuity. Therefore, we did this. Actually, using graph uniform continuity will be a tricky task. Uniform continuity is whenever two points in the domain are near to each other, the corresponding values should be near. So basically, if you look at the function, say suppose fx equals to 1 by x. In this case, what happens? Uh, what happened? Hmm. Yeah. When we have the case of function fx equals to 1 by x, a function blows up. So near 0, it, it increases very fast. Whereas if you look at the function fx equals to x, fx equals to x square in some bounded domain. In this case, the increase in the values of the range is almost similar, or we can say it is somewhere dependent on the values, change in values of the domain. So yeah, that's the only way you can see uniform continuity. I hope this is clear. So main thing is the blow up. Or what example can I give? Mm, yeah, similarly, if we take this x square in whole space R. So after when once we reach infinity, the difference in the values is very large as compared to the difference in the domain values. Okay. Is it clear, or you want me to explain with some specific example? Because yeah, understanding uniform continuity is tricky. It's not that trivial to see when the function is uniformly continuous. Okay. Uh, 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 Look at next problem. In this case, you might see what is happening. Mm, but see, we have fx is equal to root x sin x, and our domain is set of real numbers. Now, in this case, clearly we have continuity. We will show that this function is actually not uniformly continuous. So, for that, we'll be using our result. So, what was the result? It says that if xn minus yn is converging to 0, that means we have two sequences which are, even if they are not convergent, uh, after some stage, the difference between these two sequences is 0. So xn minus yn is converging to 0. So basically the difference between the points in the domain is very small, very small, and eventually going to 0. And f is uniformly continuous. Now if this function is uniformly continuous, then the difference in the values is also going to 0. So you can say it is somewhat similar to the Cauchy sequences. The difference between the convergent and Cauchy sequences is almost similar to the difference between continuous and uniformly continuous. There also, for convergence, we just saw that the sequence is converging to some one point, and for Cauchy, we look at the difference between the two terms, between any two terms after a stage. Similarly, here for continuity, we'll take one point and see whether what happens in the neighborhood of that point, whether the value at the points in the neighborhood of the that point x naught are going to some point. And for uniformly continuous, we take any difference between any two points, which gives the same, almost same or dependent difference in the values of the function. So yeah, if these two conditions happen, then should also converge to zero. Now, in order to show that the function is not uniformly continuous, we show that fx there exist sequences xn and yn such that fxn minus fyn, I mean xn minus yn is converging to zero. But so basically, I'll write it in form of p and q. So if this is p, then this is q. So basically we have p implies q. So which the negation of this is not q implies not p. That is, if fxn minus fyn does not converge to zero, then f is not uniformly continuous. So this result is cannot be used to prove uniform continuity. This result is basically used to prove not whenever to see where to show that a function is not uniformly continuous. So here we will show that there exist two sequences xn and yn such that xn minus yn is converging to zero, but this q does not hold. That means if xn minus fyn is not converging to zero, in that case f can never be uniformly continuous. So basically what is happening, the points x and yn are very near to each other. They are going towards zero. But the points fxn and fyn are not close to each other. That means the function is somewhere blowing up. Consider taking the sequence xn to be 2n square pi plus 1 by n and yn to be 2n square pi. Now the difference between xn and yn is 1 by n, which is going to 0. That means we have points which are very near to each other, but fxn minus fyn, this will be yeah, this is root x sin x na? Under root 2n square pi plus 1 by n sine 2n square pi plus 1 by n minus root 2n square pi sine 2n square pi. Mod this is equal to, we know that sine 2n square pi is always 0. So this will be taking n square common. So this will be n under root 2n square pi by n square plus 1 by n cube sine 1 by n minus 0, which is equal to 2 pi plus 1 by n cube n sine 1 by n. We know that the sequence n sine 1 by n goes to 1 because limit n tending to infinity n sine 1 by n. This is limit n tending to infinity sine 1 by n upon 1 by n. We know that this is equal to 1. So this will go to root 2 pi as n tending to infinity. Now this is not equal to 0. So the points in the domain were close to each other, but the corresponding points in the range are not that close. They are always they always have this difference of root 2 pi greater than or equal to root 2 pi. So therefore the function f is not uniformly continuous. I hope this is clear how this function is not uniformly continuous and how we used this result. So you should be able to observe the function not just by graph, because at many times the plotting functions graph is a, it's a big deal in itself, because yeah, once if you want to plot this root x sine x, that would again be a problem. Instead, we observed the values of the function. Okay, so yeah, if this is clear, then using similar this result only, I would like you to try next function and show that this is not uniformly continuous. I'm telling you the answer. Just try to look for the sequence that would be helpful in order to show that this function is not uniformly continuous. Use the same result as we did above. Use the same result to show that this function sine x square is not uniformly continuous. Try to look for some sequences xn and yn such that the difference between them is going to 0, but the difference between sine xn square and sine yn square is not going to 0. So could you find some sequences? Or okay, I'll explain. So if we take the sequence xn, xn equals to under root n pi and yn equals to under root n pi plus pi by 2. In this case, mod xn minus yn, this will be mod root n pi minus root n pi plus pi by 2. And we can just rationalize it, or no, we should not say rationalizing. Just multiply and divide by root n pi plus root n pi plus pi by 2. So this will give us root n pi plus root n pi plus pi by 2. And this will give us this is just a square minus b square, so n pi minus n pi minus pi by 2 upon under root n pi plus under root n pi plus pi by 2. And this will be pi by 2 upon under root n pi plus under root n pi plus pi by 2. Clearly this converges to 0 as n tends to infinity. We have just n in the denominator. So we got a sequence xn, we got two sequences xn and yn such that mod xn minus yn is converging to 0. And if we look at mod fxn minus fyn, this will be mod fxn minus fyn. This will be mod sine xn square. Xn is root n pi, xn square will be n pi minus sine n pi plus pi by 2. So yeah, since sine n pi is 0 and sine n pi plus pi by 2 is minus 1 to the power n, this will be 0 minus minus 1 to the power n modulus, which is always 1, which can which will eventually converge to 1, which is not equal to 0. Therefore, again, by the same result, the function f is not uniformly continuous. I hope this is clear how we use the above result to show that the function is not uniformly continuous. So again, here also the points xn and yn are very close to each other, but the points fxn and fyn are a bit far away. Okay. Okay, then next comes differentiability. So I'll just recall, we started with limit, continuity, uniform continuity, and then next we have differentiability. Limit, then we had continuity, then we had uniform continuity, and next comes the topic of differentiability. So we'll see how we can say that a function is differentiable. Hmm. Suppose f is a function defined from some subset of R to some subset of R. B, obviously firstly it should be continuous, then only we can talk about differentiability. Be a continuous function. And if I'm saying that this is continuous function, that means it is continuous at every point in x. If we say f is differentiable at some point x naught in x. Again, differentiability is a point-based property. If the following holds. If the following holds. We define a function, define a new function, define g x equal to fx minus fx naught upon x minus x naught for every x in x. If to check differentiability of the function f, we actually check the limit of this function g. So we say the function f is differentiable at point x naught uh, if if limit x tending to x naught gx exists. Yeah, the function f is differentiable at point x naught only if the function g has limit at point x naught. So I defined this new function gx just for simplicity. This is basically limit x tending to x naught fx minus fx naught upon x minus x naught should exist. That's what differentiability asks. Okay, so using this, uh, we will see differentiability of some functions. Mhm. And then we have next question. Um, if we have the function fx, which is equal to e to the power minus 1 by x square whenever x is non-zero, and this is equal to 0 whenever x is equal to 0. We need to check clearly this function is continuous everywhere because we have exponential. Only problem would have been at x equals to 0. When x tends to 0, 1 by x square is tending to infinity, minus 1 by x square tends to minus infinity, and we know that the exponential function is finite, goes to, basically it goes to 0 when x tends to minus infinity. So the function f is continuous everywhere. We need to check differentiability of this function. So we'll start with the function g. Let's firstly look at what the how the function g looks like. Define gx equals to fx minus, so yeah, in this case we need to check differentiability at 0. Check differentiability at 0. Okay, so we define the function g fx minus f0 upon x minus 0. So clearly it's given that f0 is 0. So this will be, by definition of the function f, e to the power minus 1 by x square minus 0 upon x minus 0 whenever x is non-zero. Obviously at x equals to 0 we cannot define the function g, but we need to look at the limit of the function g at this point 0. We need to check limit extending to 0 gx. So for that, we will see. Yeah, I'll tell you now. Since we know that the function exponential function e to the power x is always greater than equal to x, so that will give us e to the power 1 by x square is greater than equal to 1 by x square. Since e to the power a is greater than equal to a for every a, because we know that graph of the function exponential function is like this and fx equals to x is like this. So f e to the power x is always greater than equal to x. So this will give us e to the power minus 1 by x square. That means the reciprocal will be less than equal to minus 1 by x square. Sorry, less, less than equal to, we are taking the reciprocal, x square. So this gives us that our function g, which is e to the power minus x square by x. Different, e to the power minus 1 by x square by x. This is less than equal to x. Now this implies mod gx minus 0. This is equal to mod gx, which is e to the power minus 1 by x square by x. This is less than equal to mod x, which is equal to mod x minus 0. This implies mod gx minus 0 is less than delta whenever mod x minus 0 is less than delta. Why we did this? Because we want to prove that limit extending to 0 gx exists, and yeah, in this case it is turning out to be equal to 0. That means taking epsilon to be equal to delta, delta to be equal to epsilon, taking delta equals to epsilon, we get for any epsilon positive there exists delta, which is actually equal to epsilon positive, such that whenever mod x minus 0 is less than delta, this implies mod gx minus 0, this is less than delta, which is equal to epsilon. That means limit extending to 0 gx is equal to 0. Now since this limit exists, therefore the function f is differentiable. So the concept of differentiability now is actually dealt by using the concept of limit of for the function g. So basically differentiability is nothing new. All we need to check is the limit of this function, this new function g. So I hope this was clear how we proved that this limit extending to 0 g exists, and hence the function f is differentiable. Now you have come to a stage where uh, you can't judge a function directly by its graph. See, even for such function, we don't know how to check the differentiability, no? Yeah, if you have any doubt, please ask, or else we can move to next question. Yeah, I would. Next one, I would like you to try it yourself. Mm, Next is similar. B part. We have fx equals to x square cos 1 by x non-zero, and 0 for x equals to 0. Check differentiability of this function at x equals to 0. Okay, this is not similar, no? Mm, Maybe I can explain this one. Yeah, not okay. In this case, gx will be fx minus 0, because if at 0 is 0, upon x minus 0, whatever x non-zero. So this will be basically x cos 1 by x. We need to check limit x tending to 0, x cos 1 by x. So can you tell me what will be limit x tending to 0, x cos 1 by x?
0.
Yes. How do we prove that?
Like cos 1 by x value, it can take the values from -1 to 1. So
Hmm.
when x tends to 0, so its value must be in between -1 to 1, and it is multiplied by x, which is absolutely 0. So 0 into some value gives us 0, something like
So
this.
basically, we are using this squeeze theorem or the sandwich theorem, no? It's in between two functions which are converging to 0. So yeah, since cos 1 by x is between -1 and 1, so x cos 1 by x will also be in between -x and x. We can prove this for x positive and negative as well. It's not just multiplying the function, everything by x. So yeah, now we can use this squeeze theorem or the sandwich theorem, since limit x tending to 0, minus x is equal to 0, and limit x tending to 0, x is equal to 0. This implies by squeeze theorem limit extending to 0, x cos 1 by x is equal to 0. Now, since this is equal to 0, this implies limit extending to 0, gx exists and it is finite. Therefore, the function f is differentiable. I hope this is fine. Then I would like you to try yourself. Next problem. Fx is equal to x cos 1 by x when x is non-zero, 0 when x is equal to 0. Just check the differentiability of this function. And also, if you want some specific topics to be discussed in next class, I mean problems related to some specific topic, because we do not have exact assignments, so I don't know what type of problems you want me to discuss. If you can tell me, yeah, then only I can prepare accordingly, or else I'll do whatever material I have.
Excuse me, ma'am.
Hmm.
For this question, if I'm defining gx,
Hmm.
so here ultimately we'll get gx as like when I'm going to take the limit, it will be limit of cos of 1 by x.
Hmm.
So this value will be in between -1 to 1 when x tends to uh, approaching to 0. So it will be what value it is going to give, some specific value k. So that too we
Mhm.
don't know. So what
Mhm.
should we write? It is differentiable.
No, the function, this gx will be cos 1 by x, and using sequential criteria, you can show that this function, this limit extending to 0, gx does not exist.
Because we are not going to get a finite, because it is going to be oscillatory, no?
Exactly, exactly. So
uh,
if you look at the set cos 1 by x, x in R, so this will be -1 to 1 close interval. So basically, for any point in between -1 to 1, this cos 1 by x can converge to that point. You can always find sequence xn such that cos 1 by xn is converging to alpha for any alpha lying in this interval. So yeah, but that contradicts the uniqueness in the required in the sequential criteria. So eventually,
uh,
this will not be differentiable. Okay, I'll explain it detail in detail. I'll write it. Okay. So yeah, till here it is fine. Gx will be cos 1 by x. Now if I take the sequence xn to be 1 upon 2n pi, the sequence gxn, clearly this is converging to 0. So gxn will be cos 2n pi x, 2n pi, which is always 1. Now this implies that the sequence gxn is a constant sequence 1 which is converging to 1. But again, if I take this another sequence yn to be 1 upon 2n plus 1 pi. Again, this is converging to 0. And what is gyn? Gyn will be cos 2n pi plus pi. This will always be -1. That gives us this gyn converges to -1. But if the limit would have exist, then by sequential criteria, the sequences gxn and gyn must converge to same limit, which tells us that the limit does not exist. Thus, by sequential criteria. Limit x tending to 0, gx does not exist. I hope this is clear now. This is not differentiable. Therefore, the function f is not differentiable.
Excuse me, we have done that part, a test of convergence, we have done, or it is not in the syllabus here for
Which
the
test is this? The sequential criteria?
sequence, like any sequence is convergent, like we have to check that the sequence will converge or not. So that is
Hmm.
some test is there, no? Ratio test and Rebus test or
Series for
something.
series for series.
Yeah, yeah, yeah.
Hmm.
So it is there in the syllabus or it is not there?
If it is not discussed in the class, I don't think it is in the syllabus.
Okay, okay,
Yeah,
okay.
but the
Because
syllabus is whatever
in
it's done in the this course theory class,
okay, okay.
whichever topic
Well,
has been discussed.
actually, I missed 1 hour. I've joined late. That's why.
No, 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 no. I didn't discuss series questions today. I started with continuity, limit continuity, and then uniform continuity differentiability. Okay, then. Uh, yeah, in next class we'll continue with differentiability. I think it's not started in the theory classes, na? Differentiability. Okay, then also we'll see. I hope everything was clear in today's lecture. I haven't uploaded the notes yet. I'll try to upload them in this week. In this week, I'll upload all three lectures. And yeah, YouTube video, I've already given you the link. Na? Okay, then let's meet next Saturday. Thank you.
Thank you, ma'am.